Good morning. I'm Teruo Higashino from Kyoto Tachibana University, Japan. The title of today's my talk is a new problem setting for mobile robots based on backscatter-based communication and sensing. This is a joint work with the 5 faculty staffs of Osaka University.
This slide shows my self-introductions. We omit the details, so if you have a time, please read it.
So first, I will explain about the outline of my presentation. In this community, several types of autonomous mobile robots have been studied, such as the first work of Professor Suzuki and Yamashita in Shiroko Conference. Also, there exists commercial products such as Kilobot. However, those products do not consider the general Wi-Fi communication due to its high power consumptions. Generally, sensing is low power, just microwatt orders. However, wireless communication requires much power, milliwatt orders, so the 1,000 times larger than sensing. So recently, the wireless communication technology called the ambient backscatter communication has been developed. Ambient backscatter communication can reduce the power consumption to the 10,000th compared to the general Wi-Fi communications. It only requires 10 microwatt. So in this presentation, we will introduce our recent research about ambient backscatter communication based on sensing and discuss how we can set up a new problem setting for mobile robots using ambient backscatter communication.
Recently, a huge amount of IoT devices have been developed. So in the newspaper, it is reported trillions of IoT devices have been developed so far. However, only 23 billion IoT devices are connected to the internet. So what is the difficulty for the internet connection of such IoT devices? The main reason is power supply and battery replacement. I mean, if the battery lasts only 1 day or 1 week, IoT devices will not spread because it's a very dull work for exchanging the battery by hand. So spread of batteryless and maintenance-free IoT devices would make our society much smarter. So that's the reason why we are carrying out the study for creation of ultra-low power IoT device networks for context recognition of humans and objects. So, as I mentioned before, sensing is on the order of microwatt. However, the wireless communication is on the order of milliwatt. So the power required for wireless communication is 1,000 to 10,000 times larger than the power required for sensing. So if communication power consumption can be reduced to the same level as sensing, the total power consumption of IoT devices can be reduced to a few hundredths, even if the computation power remains the same. So reduction of the power for the wireless communication is very, very important. Next, I will explain about the ambient backscatter communication. Ambient backscatter communication is a communication by reflecting ambient radio waves. So it's a kind of the reflected wave communication. In the backscatter communication mechanisms, transceiver just send the carrier waves, and the backscatter tag just deflect or absorb the radio waves, then the modulated signal called the backscatter data is added to the carrier waves. At the receiver side, carrier waves can be removed, then the backscatter data can be obtained. In order to obtain such backscatter data, the power consumption is very small, about 1,000th to the 10,000th compared to the Bluetooth low energy and Wi-Fi communication. In ambient backscatter communication, two backscatter modulated signals are generated as frequency shift. The frequencies of the two signals are represented as f plus minus delta f. Here, f denotes frequency of carrier wave, and delta f denotes frequency shift width. Here we just show an example of backscatter tags. We just attach the backscatter tags just behind of the shoes. If the shoes is attached to the ground, then the frequency shift physical switch is on and frequency shift occurs. On the other hand, if the shoes is does not touch the ground, then the physical switch becomes off. So frequency shift does not occur. So we can count the number of frequency shift. We can estimate the number of steps of these humans. So generally, the state of the context is represented as a time variation of frequency shift or the existence or absence of such frequency shift. And the power consumption of backscatter communication is very small, about 30 or 40 microwatt level. Also, if we provide different frequency shift widths, such as delta F1, delta F2, delta F3, and so on, then we can distinguish multiple backscatter tags. I mean, if we provide different backscatter frequencies depths, then the different backscatter modulated signals are generated. So backscatter tags can identify multiple contexts in parallel. So we have designed and developed several types of the context recognition using the backscatter tags. We have designed, developed seating sensors, door sensors, temperature sensors, and the counting of the step sensors, and so on. We have designed and developed the software-defined radio systems. Here we omit the details. However, our software-defined radio system has the following features. At first, backscatter signals are not interfered by carrier waves. Secondly, backscatter signals do not collide with other Wi-Fi packets. Lastly, we can identify the positions and trajectories of the backscatter tags accurately. About the error is about the few centimeters. Next, I will explain about the autonomous mobile robots. First, I will explain about the commonly used model for mobile robots. The mobile robots are anonymous. They execute the same algorithms, and they cannot be distinguished by their appearances. Each mobile robot has its own XY coordinate system called a compass. The compasses of different mobile robots may be different. So each mobile robot executes the three operations look, compute, move repeatedly. Look operations allows the robot to take a snapshot consisting of the current positions of all the mobile robots. Compute operation determines the destination point of the robot in its own compass. And move operations execute the movement of the mobile robot to the designated destination. So several types of the distributed cooperative problems using the mobile robot have been discussed so far. In general, mobile robots assume that each robot does not have any memory nor communication function. This means mobile robots researchers aim to build an ultra-low power energy distributed cooperative system. As we discussed before, wireless communication requires relatively a large amount of the energy. However, the ambient backscatter communication requires relatively a very small amount of the energy. Also, the software-defined radio system can provide the rather accurate location for each mobile robot within the communication range of such a software-defined radio system. So I think that we can develop mobile robot with backscatter communication function. In such a system, each mobile robot can sense a specific frequency shift for the backscatter signal. So under these assumptions, I will explain about a new problem setting for autonomous mobile robot using the ambient backscatter communication. First, I will explain about the features of ambient backscatter communication. Each backscatter tag can communicate with other backscatter tags with a few meters distance. So, longer communication distance can be achieved compared to Kilorobot. Kilorobot has a communication using the wing-flared communication, and the communication distance is about a few centimeters. Also, the two transceivers can provide the location of each backscatter tag with a few centimeter distance errors. Also, transceivers can emit carrier waves only for specific cells using the beamforming techniques. This is a feature of ambient backscatter communication.
So we can consider the following model for mobile robot using backscatter communication. If each mobile robot has its own specific frequency shift width, it can know its own position with high accuracy. However, it cannot know the positions of its neighboring mobile robots, because each mobile robot has its own specific frequency shift width. On the other hand, if multiple mobile robots have a common specific frequency shift width, and if those mobile robots ask their own location to a nearby software-defined radio system asynchronously, those mobile robots can know their positions in parallel. However, sometimes packet collisions might occur. Since each software-designed radio system has its own communication range, and a large number of mobile robots cannot have the common frequency for the frequency shift in real situations. So, each mobile robot can only know the location of a small part of its neighboring mobile robots at different times. That's a little bit difference between the mobile robots using the backscatter communication and the mobile robots using the general assumptions.
So, by detecting the directions of the radio waves from two base stations, the exact position of a target backscatter tag is known at the intersection of the two directions of the radio waves. So if two backscatter tags receive the radio waves from the same two base stations, their positions and scales can be considered under the common XY plane and scale. For example, at the right side figures, there are four green nodes. Those nodes receive the backscatter signals from the BS1 and BS2, and it constructs the common XY plane called the plane 1, 2. However, if two backscatter tags receive the radio waves from different pairs of base stations, their position and scale cannot be considered under the common XY plane and scale. So that there are three purple nodes at the right side figures. Those nodes receive the backscatter signals from BS3 and BS4, and it constructs the common XY plane called the plane 3-4. And plane 1, 2 and plane 3, 4 are different scales and different positions. So the problem is how can we estimate the common XY plane and scale for all the backscatter nodes? So under the assumption, only mobile robot accessing the same base station pair can agree on the XY plane, it will be an important issue to consider the problem for finding a common XY plane for all mobile nodes and for getting the consensus among them. It's a new problem for this kind of the models. Also, if each mobile node has backscatter tags and a mobile robot can communicate with other mobile robot with backscatter tags, here each backscatter tag can control the direction of the signals. In such a case, if we include the backscatter communication for mobile robot, we might need to modify the basic look, compute, move cycles, such as look, compute, communicate, compute, move cycle, and so on. So we might be able to consider the new swarm computing algorithms.
Also recently, the beyond 5G technology are actively studied. For example, the NTT DOCOMO and AZC announced that they have developed a prototype technology which efficiently guides the 5G radio signals received from the outdoors to the specific locations indoors using the film-like metasurface lens. Those technologies can control the direction of the signal so that only the users and the devices in the specific cell areas can receive the signals. Such technology also gives us some hints for considering the new problem settings of autonomous mobile robots. So, lastly, we conclude my talk. In this presentation, we have introduced our recent research about the ambient backscatter communication-based sensing and discuss how we can set up a new problem setting for mobile robots using the ambient backscatter communication. So we hope that researchers in this community can find some hints from recent research about ambient backscatter communication and beyond 5G technology.
So thank you very much. If you have any question or comment, please send me email.